Good afternoon, everyone. Today, my topic of discussion is primarily is going to be revolved, around voltage to current converter and current to voltage converter. As you can see that both the names suggest it is a kind of vice versa condition, right? So here it is a kind of converter which can you know convert the voltage signal into the current signal, and here it is just the opposite case. So first of all, I would like to share with you that these two converter has certain a distinct name, an additional distinct name. So sometimes it may happen that you are not directly told to describe about voltage to current converter, but better you may be asked to give a brief idea or brief description of transconductance amplifier. So this is a special kind of name it is given. This is a transconductance amplifier, and similarly this current to voltage converter is called transresistance amplifier. Okay. So why this is a kind of name it is being associated with the circuit that I will gradually point out. So before going to that conclusion, first of all I would like to give a brief description about how these two converters are going to be worked. Now, if I start with this voltage to current converter, then I should mention that whenever we are going to describe about the operating principle of these two converter circuits, then also for each case you know, we need to show the operation in two different circuit diagram in each case, right? What are those two cases? For voltage to current converter, for V to I converter, the circuit diagrams contain the two operational amplifiers. One is with floating load, another is with grounded load. Now, what does this mean? I'm coming to it. And for current to voltage converter, we need to describe the operation of this I to V converter using inverting mode and as well as non-inverting mode. So in each of these two cases, you can see that we need to describe the operation of this converter circuits with two distinct circuit diagrams. Now I am starting with this voltage to current converter circuit, right? So first of all, I am going to draw the circuit diagram with floating load. With floating load. First of all, let me draw the circuit first. Then I am going to tell you what is all about this floating load. See, this is the inverting terminal. I have given one resistance. This is RS. And here from the non-inverting terminal, I am applying an input Vi. If I say this is my node A, I am giving one feedback resistance RF, and this is your view. So this is my circuit with floating load. Now what does this mean by floating load? See, this is your load. If I say this is my feedback resistance, so this is basically the load. This is basically the load impedance, I can say ZL. I can term it as ZL. So whenever a particular load which is connected from the output to the input side. So whenever this out, I mean, whatever be the load resistance or load impedance, you can say, which is connected at the output side, if this is not connected directly to the ground by some electrical connection, then I can say that this load is floating in nature. And if I make this particular load resistance to the ground by an electrical connection, then I can say that the load is grounded. Fine. So here you can see that this load, this ZL, or you can say this RF, is not connected with ground directly, right? So that is why I can say that this is the V2I converter circuit, V2I converter circuit with floating load. Now, since we know that the differential voltage between two terminals, we always, you know, keep this particular voltage as zero. That means obviously whatever be the input voltage here, that must be equal to the voltage at node A also. So I can write that VA must be equal to VI, right? So if I give this equation as number one, then you can see that what I can write as IL, that means the load current. If I say that this is my load impedance or load resistance, you can say, so that means, we are applying a positive voltage source at the non-inverting output, non-inverting input terminal. So automatically my output will be you know, the greater version of what we have in the input side, because we know that for non-inverting amplifier, output voltage VO equal to 1 plus RF by R1 into V in. So automatically I can I can tell you that if I make this particular terminal is grounded, that means automatically this must be at lower potential and this must be the higher potential, the output terminal side. So obviously the current must flow into this direction, and obviously whenever it reaches at this particular point at node A, obviously due to the infinite input impedance, no current can flow to this side. So I equal to 0 here basically. So the whole amount of current IL must be flowing across this I mean the series resistance or input resistance, you can say RS, and it is going to the ground. So automatically if you look at this particular region, if you look at this particular region, you can see that this is the similar current which is flowing across the load resistance as well as this resistance RS. So I can write this IL from this particular point, that this IL equal to nothing but VA minus 0 by RS, because obviously you can understand that node A must be at higher potential in comparison to the ground potential. So I can write that this IL is nothing but VA by RS, right? So I can write that VA equal to RS into IL, and obviously from where we can write that, you can see that I can write this VI equal to RSIL from equation 1, because we know that VA equal to VI. So you can see that this IL is nothing but VI by RS. IL equal to VI by RS. I can write here better. IL equal to VI by RS. Fine. This is it. So now you can observe that even if it is a load current IL, right? Even if this is a load current IL, this is, independent of load resistance. That means I have never, you know, incorporated this RF because this is not at all necessary, right? This is not at all necessary to, establish the expression of the load current. This is all about it is dependent on the input voltage as well as you know, the input resistance. So this is the circuit of the VI converter with floating load. Now coming to the grounded load. So if I say that I need to design V2I converter with grounded load, now I should keep in mind that I need to connect my load resistance or load impedance, whatever you can say, with ground through some electrical connections. So let me draw first the circuit. I had one resistance. Here also I have one resistance. And I make it this is ground. I have another resistance here. And obviously I am supplying input voltage to this non-inverting terminal. From here, the situation is slightly different. Here I have as it is my feedback resistance, but here this is not the load resistance, right? This is not the load resistance. So where is the load resistance? Load resistance is here. I am giving it as load impedance, right? So if I now denote which one is what, so this is your resistance again R. If I say this is my VI and if I say this is my I1, so basically I am trying to say that this I1 must be also flowing across this because we know that here I equal to 0. Here I equal to 0, right? So no amount of current can pass through this region due to having high input impedance, almost infinite input impedance. So that is why, you know, we require a particular, I1 to flow into this direction from here. And let's say I am I name it this node as A right now, not this one. This node is A, my node A. Here also, let's say I am having another current component which is I2 that is coming from this location, and here we have IL. Mind it that this has two distinct connection. This is RA, this is, it is having another connection. So basically this two terminal is connected with this output terminal. I'm just trying to say this. That means this is not the same, wire that is coming from RF and here. That is what I am trying to say, because in both case the way I draw the particular figure, these two are getting overlapped. That is why I am trying to mention that this is basically the two connections is basically connected to the output voltage terminal, right? So now if I apply KCL, if I apply KCL at node A, if I apply KCL at node A, what should I get? We get I1 plus I2 equal to IL. Can you see this? If I apply KCL at node A, I1 plus I2 equal to IL. So what is your I1? I1 is nothing but, see, this is your VI. This is the I1 current, which is basically, coming from this VI, and it will reach at this node A. So, and obviously this R is the resistance, located, between this particular path. So I can write for this I1 as VI minus VA by R. This is for I1. This is for I1. VI minus VA by R. Fine. For I2, what we can write? We can write similarly that VO minus VA by R. Similar thing. So I should write VO minus VA by R. That is equal to IL. Now I'm going to just simplify, right? IL equal to, I'm just going to simplify it. VI minus VA plus VO minus VA. So automatically you are getting VI plus VO minus 2VA whole divided by R. This is your IL, right? Or if change the side, you can write that minus 2VA, this one, minus 2VA, this one, is RIL minus VI minus VO. RIL minus VI minus VO. Or this VA equal to, I'm going to, change the sign, because here I am going to just, you know, shift this minus sign to this, from the left hand side to the right hand side. So this minus VI becomes plus VI, this minus VO becomes plus VO, and this plus RIL is becoming now minus RIL whole divided by 2. Just give it the number 1. Now you can see that what we have done in the, different, instrumentational amplifier, like whenever we have done the last part of the differential amplifier, which appeared as a non-inverting amplifier, right? So here also you can see that this is also, a non-inverting amplifier, I can say, because the input voltage is applied to the non-inverting terminal. So you can see that what is the input voltage here? Is it VI, which is coming to the terminal, positive terminal here? No, because there is a certain, feedback. There is a certain kind of, feedback, which is basically coming into this particular terminal, which is nothing but this VA. That means the input voltage, that means the voltage at node A, which is basically, the voltage that appears as an input voltage to the non-inverting terminal. Now if this is so, then When we can see this particular op amp as a non-inverting op amp, then I know that for any non-inverting op amp with input voltage is VA as the voltage applied at non-inverting terminal, even if even if it is having a supply voltage of V in which is connected to the non-inverting terminal, we can say that this output voltage VO, then the output voltage becomes VO equal to how much for non-inverting op amp? I should write the gain first. 1 plus RF by R. Why I am not writing R1? Because here in the picture I have given R. That is why. That is why RF by R into VA. Right? Because every time the output voltage must be equal to 1 plus RF by R1 into input voltage to that non-inverting terminal. But here this voltage is VA, not V in. What will be the supply voltage right now? So if I consider that RF equal to R, then I can say that the gain will be 2 and output voltage VO will be how much? 1 plus 1 into VA, because RF by R, that means 1 plus 1, that means twice of VA. Now from equation 1 we are going to substitute what is my VA. So if you go on substituting here, the 2 into, now VA was VI plus VO minus R into IL whole divided by 2. So you need to write here by equation 1. So this 2 will be cancel out and you will get VI plus VO minus R into IL. And here you will have VO. Again, this VO will be cancelled out and you will only get RIL equal to VI, or IL, the load current, is equal to VI by R. And you will again get to see that here also load current is independent of load resistance. That is why the circuit is known as constant current source, since Vi is constant here, right? Vi is constant, so it is providing you the constant current source, and also the fact is the load current is independent of load resistance. That means this load current does not, or the output current does not depend on load resistance. Since this is the voltage to current converter, so automatically the output signal must be current. So output current does not depend on load resistance. Very, very important conclusion of the voltage to current converter. And another thing you can see either from here or from the final expression of the V2I converter with floating load, either from here. For both the cases, from both the expression, you can see that this IL is proportional to 1 by R, 1 by resistance, right? Here also you can see hmm, that IL is proportional to 1 by R. So that is why this circuit is known as transconductance. That means 1 by resistance. That is what that means the reciprocal of the resistance. That means the transconductance, and the circuit is hence known as transconductance amplifier. So that is what is voltage to current converter all about. Now coming to the second amplifier, the next you know type of amplifier, which is nothing but the I to V converter, that is the current to voltage converter. If I talk about current to voltage converter, then I know now that this particular you know uh, converter is also called as trans resistance amplifier. So if you go on following the this condition, the trend, that means here obviously the output voltage must be proportional to the resistance. That obviously we must have to observe to justify this particular name, that is it is called trans resistance amplifier. So we will obviously see that. But before reaching to this particular conclusion, we first like to observe how we can formulate the output voltage, because this is the current to voltage converter, so automatically output signal must be the voltage one. So how can we formulate the expression of the output voltage? By using two different circuit diagram in association with two different op-amp modes. One is inverting mode, another is non-inverting mode. So first of all, I would like to draw the circuit diagram using inverting mode. Circuit diagram of I to V converter. This is my current source, current to voltage converter. So here is my current source. In parallel, I have one resistance. Let's say this is my input resistance R. Let's make it ground. This is coming to your inverting terminal. From here, we have one feedback resistance. This is my output voltage. Non-inverting terminal, it must be grounded because this is the inverting mode. So you can see that I have applied the current source, that is, you know, which is the input of this particular converter circuit, to the inverting amplifier. So now if this is the node A, I can write that this is the voltage at node A, can be denoted by VA, and all of us know now the concept of virtual ground. So due to virtual ground, we can write that this VA must be equal to 0, since obviously these two terminal should have the similar potential. So automatically this terminal is directly grounded. So automatically this must be at 0 volt. So automatically this VO must also be 0. So if it is so, then automatically the current through R1 is also 0, right? Current through R1 is also 0 because VA is 0. So only thing what is appearing as a current in this particular circuit is due to only because of this current source. That means due to this current source, only this II amount of current is going to flow here, and automatically this II is going to flow through RF as well. That means if I say that this is also the current, so this I can write this feedback, current across this feedback resistance. This particular current, I can term it as this is the II. This is the II because here basically we are having voltage VA equal to 0, and obviously we know that no amount of current can you know pass across this particular terminal. Here basically we have I equal to 0. So obviously the whole amount of current must be flowing across the feedback resistance RF. So I can write that this II is nothing but IF, what I have just mentioned. So what is it? It is nothing but VA minus VO by RF. Why I am writing in this manner? Because obviously I have applied the source to the inverting terminal, so automatically my output voltage must be of lower potential, because we know that for inverting terminal, inverting op amp, output voltage VO must be minus RF by R1, which is the gain, multiplied by the input, right? So obviously this VO must be having the lower potential as compared to VA. So I can write that this II is nothing but, that is why the current is flowing in this manner. So I can write this II or IF is nothing but VA minus VO by this resistance RF. So if it is so, then I can write that this II is nothing but minus VO by RF, since we know that this VO equal to 0, right? Or this output voltage, because this is a current to voltage converter, so automatically output must be the voltage signal. So voltage, output voltage VO is nothing but minus IIRF. This is your final you know expression of I to V converter using this inverting mode. And you can see here that to satisfy this particular name, that is the trans resistance amplifier, you can see that the output voltage is proportional to the feedback resistance. So automatically it is very much proportional to the resistance, feedback resistance. So automatically I can say that on the contrary, um, to this V to I converter, so here the output voltage, or output signal very much is very much dependent on the feedback resistance, right? And you can see it is you know dependent in proportional. So that means in what manner we are going to change this RF, VO will change accordingly. So this is one circuit using this inverting mode. And now I am going to show you the same operation, current to voltage converter, using another circuit, which is the non-inverting mode. If you are not mentioned in the question that you are whether you are going to follow the inverting one or non-inverting one, if you are straight away asked to describe the operation of I to V converter, you will have to show the both the modes. The same is applicable for V to I converter as well. So by using non-inverting mode, we know that non-inverting amplifier connection. That means now we are going to make this inverting terminal grounded, because this is non-inverting mode. So automatically I'm going to you know apply the input signal to the non-inverting terminal. So this is current to voltage converter. So automatically it must be a current signal like II. This is what I want to fade. And from here I'm going to apply one input resistance, so that at this particular node I can create one input voltage Vi as, this is the current and this is the resistance II into Ri. Why? Because, just let me finish first the diagram. Okay, because we know that here we have I equal to 0, here we have I equal to 0. So if it is the current signal, so automatically this current must be flowing in this manner, right? It cannot go beyond this particular point in this region, since this op amp is having, infinite input impedance, right? So that is why this current must be flowing across this. So automatically through Ri it is flowing, so automatically it will creating a voltage drop across this resistance, and it appears at this particular node as Vi equal to Ii into Ri. Now, since we have the particular, concept like vd equal to, 0, that means automatically here, if I consider that this at this particular, terminal as it is, this vi, appears here. This is also, vi, right? If I say this is my R1, so automatically both the voltages must be, equal, and at this node A, obviously we will have this, vi as well. So in that very manner, what would be your, output voltage, because this is a non-inverting terminal, non-inverting op amp, so automatically vo must be 1 plus rf by r1 into vi. This is the input voltage what we have created in this manner. So if I, just, mention, or if I just substitute what is my vi, because we can see that vi equal to ii into ri. So if I just go on substituting vi here, then I can have 1 plus rf by r1 into ii into ri. So this is your final expression. This is your final expression of output voltage, where you can see that again your output voltage is proportional to your resistance, either this ri, or you can see that here also vo is proportional to this feedback resistance as well. So basically, in that very case, you can understand that this is the current to voltage converter. If you go on change your input, current, then you are also, and here from here also you can see that this vo is also proportional to ii, and here also vo is proportional to ii. That is also, you can see, this is another observation. So if you go on changing your current, obviously you are getting, the output voltage as it is, because here there is no such independency on the feedback resistance or any kind of, input resistance. These voltages are very much, dependent on the resistance, and that is why you can see that there is a, a straight away proportional relationship between the voltage and resistance, and that is why this particular converter circuit, which is the current to voltage converter circuit, is known as trans-resistance amplifier. So this is all about your general overview of, voltage to current converter and current to voltage converter. So that's all. Thank you so much.